Hello and welcome to lesson 39 of my DP chemistry curriculum. We're going over structure 2.2.2. What that goes over is single, double, and triple bonds involving 1, 2, and 3 shared pairs of electrons respectively. So we'll explain the relationship between the bonds, bond length, and bond strength by the end of this, as well as learn how to draw them. So without further ado, let's go into multiple covalent bonds. So from our last lesson, we learned that whoops, already messing up. Covalent bonds are shared pairs of electrons. Shared pairs of electrons. So what I mean is if we have hydrogen sharing with another hydrogen or fluorine sharing with another fluorine, now fluorine is going to have a full octet, while hydrogen did not due to the fact that it only has the s orbital, it can only have a duet. But either way, we have these bonds right here, that one and this one. These are a shared pair. We call this a single bond. And generally, we actually reference them with Lewis diagrams looking a bit like this, where I'm using lines to represent the pairs of electrons, including the bond. But sometimes we cannot complete an octet with just one bond. So sometimes octets cannot be made with one shared pair. So let's look at an example where that's the case. If we look at oxygen, which has 6 valence electrons, 1, 2, 3, 4, 5, and 6. We put it next to another oxygen, 1, 2, 3, 4, 5, 6. Unfortunately, this only has 7 valence electrons, and this now only has 7 valence electrons. So it's not complete. So we realize that we can do something else. We've got these two lone electrons. They're not in a non-bonding pair, but they could become a bonded pair. So what we do with this is we just join them together. We go like that. And now both our oxygens have 8 valence electrons if we look at these as groups. So we got 8 here, and we got 8 here. And we now refer to this as two shared pairs, which, if you can count, that's 4 valence electrons. So a single bond only has two, but now what we call a double bond will have four paired valence electrons. And so we can represent this with our Lewis diagrams like this. And we use two lines. So that's still two shared pairs. And that's what we call a double bond. However, sometimes two is not enough. If we take another example of nitrogen, which has 1, 2, 3, 4, 5 valence electrons, and we put it next to another nitrogen with 1, 2, 3, 4, 5 valence electrons, neither of them are complete. This one only has 6, and this one only has 6. So why don't we add another? Let's double it up. 2, 3, 4, 5 valence electrons, and N 1, 2, 3, 4, 5 valence electrons. It's still not complete. So the double bond didn't work, but we notice we still have these little stragglers. We have these lone electrons, and the truth is we're never going to end up with lone electrons. They will either bond to something else or create that triple bond or create whatever. They're going to create a bond. So we actually move all the way over to 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. And now we can see that we have 3 shared pairs. And within this 3 shared pairs, we have 6 valence electrons, which this is called a triple bond. And so we can once again just draw this a little cleaner. 3 with those pairs on the side. So that's how we use single, double, and triple bonds. But you might now have a question, well, how do I draw more complex structures other than these simple diatoms? So we have new rules for drawing with multiple bonds, but it's pretty much the same as before. Drawing with multiple bonds. I mentioned in my last video, step 4 was to check the structure. And I said there's going to be a change when we have more bonds, and we'll see that change today. So step 1 is still going to be calculate our valence electrons. So you should be practicing that. With step 2, identify central atom and draw skeletal structure. Draw skeletal formula with single bonds. So it's still the same step here. We still only use single bonds in our skeletal formula. We're not going to predict double and triple bonds yet. Step 3 is to add remaining valence electrons. And then step 4 is check structure. So this is all the same. And step 3 is add remaining valence electrons as non-bonding pairs. So it's exactly the same, except step 4 has a second part. When you check your structure this time, you're going to notice there are non-complete octets. So if there aren't enough valence electrons to complete octets, which there won't be often, octets, what we do is we move a neighboring non-bonding pair to become a double, or if needed, triple bond. So I'll show you how this whole thing works step by step. So let's do an example with carbon disulfide. So take a moment and try and figure out what the structure of carbon disulfide is and what its molecular formula. And I'll answer that now. So carbon is C, and disulfide, sulfide refers to sulfur, and di refers to 2. So we're looking at CS2. So we'll go through our steps. Step 1, valence electrons. Carbon has 4, sulfur has 6, sulfur has 6, for a total of 16 valence electrons. Step 2, our central atom is going to be carbon. There are fewer of it. And not only are there fewer, it's on the furthest left side of the periodic table, and it's written first. So I will draw the skeletal structure, bonding it with single bonds. Step 3, I'm going to add our remaining valence electrons. So I've used, so far, 2 and 4. So I need to use a total of 16. So I have 12 more valence electrons to go. 2, 4, 6, 8, 10, 12. Perfect. Step 4, I'm going to check our structure. So I notice this has 8, so it's good. This has 8, so it's good. But carbon only has 4, so it's not good. When I'm counting the valence electrons. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4. So carbon is not good. So what I need to do is I need to do a little bit of moving. If I move this one here and I move this one here, then I create this new structure that looks like carbon with 2, or whoops, move that one, carbon with 2, and now I can count again. I have 2, 4, 6, 8. Sulfur is good. Carbon 2, 4, 6, 8. Carbon is good. 2, 4, 6, 8. Sulfur is good. This is my final drawing of carbon disulfide. And so we can just move those non-bonding pairs to help out and complete the picture like we did here. So Now that we've been able to practice a regular one, let's do one more practice, but let's practice a polyatomic ion, so Cn minus cyanide. So what we're going to do is exactly the same steps as before, but if you remember from polyatomics, we had a step after calculating valence electrons. It was to add or subtract for charge. We also had a final step at the very end, which was adding a bracket with the charge. And we're still going to do the exact same thing. So step one, we're going to do our valence electron check. Carbon is 4, nitrogen is 5, which is 9. But now we're going to add 1. So we'll add 1 from that electron right there, which is going to give us a total of 10 valence electrons. Step 2, we'll do our skeletal structure. There is no central atom because there's only 2 atoms. Step 3, we're going to add those valence electrons back. We've used 2 already, so 2, 4, 6, 8, 10. That's all the valence electrons we get. Step 4, we're going to check. Now carbon only has 4 here, while nitrogen has 8. So that doesn't work out. Carbon needs 2 more pairs of electrons. So I'm going to move 1 pair and then another pair. And I will get that our final structure looks like this. C, 1, 2, 3, N. And now the final step, step 5 for polyatomics. All right, let's switch off blue because we already used that one. Step 5 for polyatomics is we're going to put brackets around this and the minus charge back. So that's our cyanide structure right there. It has a triple bond. So that's how we draw these. The last thing we need to know for this lesson is how to compare these bonds. So let's compare bonds. And single, double, and triple bonds differ in a few different qualities. The first we're going to look at is bond strength. When we look at the strength of a bond, something we have to remember is these are just the electrostatic forces. Electrostatic forces between nuclei, whoops, nuclei and shared electrons, or shared valence electrons. We should be clear about that, but of course they're the valence electrons. And generally, if we have more shared electrons, we have more attractive forces. More shared electrons, more attractive forces. If we were to draw this out, we can see 2 nuclei here on opposite ends of some electrons. 1, 2, 3, 4, 5, and 6. So that would represent a triple bond if we have 6 electrons. And what we see is an attractive force between the nuclei and each electron. And we have quite a few attractive forces here because each nuclei is going to be pulling pretty equally on each of the 6 shared electrons. Meanwhile, if we take this diagram, duplicate it, and we get rid of a few of these electrons, like let's say 2 on the top and 2 on the bottom, we notice that there are less electrostatic attractions and less attractive forces. So we can see that more bonds is equal to a stronger bond, which kind of makes sense. If you tie 1 piece of rope versus 3 pieces of rope to something and they're the same size rope, you would assume that 3 pieces of rope would hold it better than 1. It seems like a very obvious concept, but it's something you got to be able to recognize right away. The other property we're going to look at is bond length. Generally, when we look at things like atomic radius, which we already noticed, a smaller atom has more attractive forces. And the same things here. If we have more attractive forces, we can hold closer together. Therefore, we can find that in terms of length, triple is shorter than double is shorter than single. However, the number of bonds is not the only thing that can affect it. So not all bonds of the same kind are equal in length. In length. If you look at hydrogen bonded to hydrogen versus chlorine bonded to chlorine, well, bond length is actually defined as just the distance between bonded nuclei. And this one, hydrogen bonded to hydrogen, is the overlap of two s orbitals, which is going to be a very small distance. While chlorine bond to chlorine, while it still might be some orbital overlap, we have three energy levels that need to overlap. And for that overlap right here, we're going to have a much greater distance between the chlorine and chlorine. So if you need to know specific bond values or specific distances between atoms, those values will be found within your data booklet for the DP Chem exam. All right, the last property we need to know is, whoops, not bond, electron density. And this one is going to be the most obvious out of all of them. More electrons equals more dense. What we're saying is that a triple bond has a higher electron density than a single or double bond. And that's very obvious, but it's something we're going to come back to later as we start talking about the geometry, the shapes that atoms form. And we need to look at electron density and figure out which areas are more electron dense. This is also going to come back in organic chem as well. So while seemingly very obvious, it's something we need to be constantly looking out for. So anyways, I hope this helps and have a great